Another type of statistical tests that are used much more frequently in psychology compare two empirical distributions or compare two samples. And the questions can be different. For example, if the samples are independent, we can ask the question, are the scores on anxiety the same or different in the samples of males and females? Or is the academic achievement the same in psychology students and sociology students, for example? Or if we have dependent or related samples, we can ask the question, did the anxiety score change from before to after the intervention? So was our intervention effective in changing these anxiety levels in patients? So all these hypotheses test the same type of general hypothesis. Hypothesis H0 states that distributions in these samples come from the same general population, come from the population with the same properties. And H1 states that distributions come from different populations. And we say that the properties of these distributions are statistically significantly different. So if you have a significant p-level, then you can reject H0 and you can say that there are statistically significant differences between these two distributions. And here we have different situations. If you have two nominal variables, for example, gender and favorite color, then what you apply are statistics for cross tables, and you use an approach which is called cross tabulation. You basically create a table and you count for each person, for each type of people, like males and females, how many are there with each type of color preference. And in SPSS, all these analyses live in the menu under Analyze Descriptive Cross Tabs. And there you can calculate different statistical tests. The test that is used most often for independent samples with more than 2 levels, the most universal test is called chi-square test, which we can encounter most often. For example, we can ask the question, are the color preferences the same in male and female participants? And then, of course, we apply chi-square tests. But very rarely you might have a situation when you have dependent samples. And then you can use Cohen's kappa or some other statistic for dependent samples. And in some situations you have a table which has 2 levels and 2 levels on both variables. For example, male, female, and successful, not successful on some kind of outcome. And then you can use more simple statistics like Fisher exact probability or Guilford's phi correlation between 2 binomial variables to estimate this association or difference. Here, essentially, association and difference between samples is the same. Is there an association between gender and success, or other differences between males and females in the probability of success? This is essentially the same question, and it is tested with essentially the same statistical test. So I will not go into details on these particular statistical tests because you're going to take a look at them in seminars. I will just give a little warning concerning chi-square test, because very often people misapply it. And whenever we apply chi-square tests, we need to be aware that it has some important assumptions. First, that in your table, the values in different cells of your table come from different individuals. They are not related in any way. And also that expected values in those cells of your table should not be very low. if you have several cells where your expected and observed values are very close to 0, chi-square test might be wrong. It might give you false positive conclusions. That's why you need maybe to collapse similar answers into larger categories, or just exclude some categories from analysis in order to meet these assumptions of chi-square. Because I've seen in research papers when people applied chi-square test to dependent samples, to a situation when the values in the cells were related, they came from the same individuals. And this is completely wrong, because it basically would lead to mistaken conclusions. If you have dependent samples for nominal scale, for example, you have 2 experts who classified objects into 5 different groups, and you might be interested in agreement between those experts. Then what you use is normally Cohen's kappa. However, Cohen's kappa is only good for 2 experts. Usually you need to have more, and there is now a much more universal statistic called Krippendorff's alpha, not available in SPSS, unfortunately. But if you need it, you can always Google it up. So this is a fairly rare situation, and I'm not going to talk about it. A much more frequent situation, which you are going to encounter definitely in practice, which you are going to encounter whatever topic your master's dissertation is about, is comparing samples, comparing 2 groups on an ordinal or interval variable. For example, are anxiety scores the same in males and females? Or do males and females in your sample have the same average level of education? Or did the scores change from before intervention to after intervention? And these are the types of questions that you answer with help of either student t-test, if you can use a parametric test, or with help of its non-parametric alternatives, such as Mann-Whitney or Wilcoxon tests. Here you can see where these tests live in SPSS. It's easy to find them in the menu. Let's take a little bit of look at the student t-test. Why is it even called student t-test? Actually, it was not invented by a guy called Student. It was invented by this statistician called William Seeley Gossett, who worked at Guinness Brewery. And he was interested whether beer from different batches had statistically different properties, and in other questions like this. But unfortunately, because he was working in a Guinness Brewery, his contract did not allow him to publish papers under his own name. That's why he used the nickname Student for his paper where he published this statistical test, which quickly became extremely popular because it was extremely simple and handy. So whenever you conduct students' t-tests, think of something nice like Guinness beer. There are different versions of student t-test for independent and for dependent or related samples. They are extremely similar in terms of the assumptions they make and in terms of principles that we interpret them. However, they make different assumptions about data. So the version for dependent samples is less strict, so don't confuse them. Make sure you choose the right one. So what are the assumptions of student t-test? Well, the first assumption is normality of distribution on your dependent variable. For example, anxiety scores are supposed to be normally distributed in your sample as a whole and in each of the groups you are trying to compare. And another assumption is called homogeneity of variances. It is an assumption that standard deviations or variances in those groups do not really differ very much. So if standard deviations in your groups are comparable, you probably have no problems. But if in one group you have a standard deviation of 1 and in another group it's 10, then definitely you might have a problem. And basically, comparing a group with a very narrow distribution with a group with a very wide distribution, it's easy to make a mistake. And this assumption is tested with a separate test called Levene's test, which basically compares variance or standard deviation in both samples. And if Levene's test is statistically significant, it means that there is a difference in the size of standard deviation between two groups that cannot be ignored. And another little life hack is that student t-test has the highest statistical power in case when your groups have comparable sizes. Of course, you don't have to compare groups always of equal size, but if one group is very small and another one is huge, your ability to detect significant differences will be somewhat lower. That's why when we conduct, for example, experimental studies, we try to achieve balanced groups of comparable sizes. So the student t-test in SPSS lives in analyze, compare, means, and here you have independent samples t-test and also paired samples t-test. And for one sample, there is one sample t-test which can compare expected mean to observed mean. Yeah, so let's take a look at the independent samples t-test. I use this demonstration dataset, which is basically a bunch of psychological measurements from obtained from students who have different characteristics. They have different gender, and they also came from different regions. And also they were admitted to the university on different bases. Some were admitted on the basis of regular exams, and some were admitted on the basis of academic competitions. And here we can compare whether motivation characteristics, whether the scores on intrinsic and integrate motivation are different in the groups of students who were admitted based on normal exams and admitted based on an academic competition, Olympiad. That's why this variable is called Olymp. It's nominal, and when we compare scores in groups, we here in test variables we add the variables that we want to compare, as many as we want. And in grouping variable, we set this variable which differentiates between our groups. So this Olymp variable we place here, and we also need to click on define groups and to tell SPSS how are the groups coded that we want to compare. Because you might have more than two groups on this variable, and you might just want to compare two of them using student t-test. That's why you need to tell here to set the values which code the groups. And in our case, it's 0 and 1. And then you press continue, and you simply obtain this table with results. The tricky point about this SPSS output is that the first part is for Levene's test for equality of variances, whether the variances in the groups are equal. And here it's not significant, which means that we can assume that the variances in the two groups don't really differ very much. Normally you just ignore this part, and you need to look at the second part, which is exactly the results of student t-test. So you have t statistic, which is compared against theoretical distribution. You have the number of degrees of freedom, which is basically your sample sizes -2. And you have this level of significance, our magic p-value. And here you see that it is significant in all cases. Now, SPSS gives us results for a normal t-test. It's easy to tell it because the number of degrees of freedom is integer. And for a robust version of t-test that does not assume equal variances. This is also called Welch's t-test. In principle, if your Levene's test is not significant, you can just use the normal t-test. But if your Levene's test is significant, which means that variances are not equal in two groups, it makes sense to look at this more robust version of the t-test, the Welch's t-test. However, recently, research has found that basically this robust version and the normal t-test, they have pretty much the same statistical power in case if variances are equal. So in principle, now people say that, researchers say that you can use by default the robust version of t-test and just ignore Levin's test. But well, it's a matter of preference. So here, as you can see, both the normal t-test and the robust t-test give us pretty much the same results. They are substantially the same, so which one to publish, it doesn't matter. But if they give you different results, probably Welch's test is more trustworthy. The problem here is that in this table we don't see any effect size. And you remember from our last discussion that when you compare two groups, your effect size is Cohen's d, which is the difference between two groups in the amount of standard deviations, in standard deviation units. And you need to calculate this Cohen's d separately. You can calculate it in Excel using a formula, or you can use an online calculator, which I showed last time, psychometrica.de, which is a fairly good one. Just be careful when you choose online calculators, because different ones can use different formulae for the denominator here for pooled standard deviation. Some just use average standard deviation, and then if your group sizes are very different, you might have a result that is not very precise. If you calculate it by yourself in Excel, you need to remember that in Excel there are two different standard deviations. One standard deviation is for a general population, and another standard deviation is for a sample. And there is a slight difference in this denominator. If your sample is large, this difference does not have any effect. But if you are comparing your standard deviations calculated in Excel and in SPSS, and if you see some difference, this difference might be because SPSS calculates sample standard deviation by default, just like other statistical packages. And in Excel, the default formula calculates population standard deviation. Not that it usually makes much difference, but if you see a discrepancy, this is due to this and not to anything else. So just when you are calculating something by hand, make sure you don't miss results from different formulae in one calculation, because then you might see some misleading results. And the very good news is that in SPSS version 27, which is the most recent as of this time, finally, Cohen's d is calculated automatically. I don't know why they did not implement it until now, but finally you can see Cohen's d here with a pooled standard deviation. However, there are also other effect sizes, for example, Glass delta, where you have an experimental and a control group. And how does SPSS choose which group is a control group? That's a good question. So also be careful about this. But at least for normal Cohen's d, we finally have a point estimate, which is minus 0.43, kind of a weak to average effect. And you also see confidence interval, 95% confidence interval, which describes the limits within which this true effect size in the population is supposed to lie with 95% probability based on our sample data. And you see that this confidence interval does not include 0, so this effect is statistically significant, but of course this significance is evaluated with student t-test. So for integrated motivation, the effect is a little bit weaker. It's minus 0.37, and the confidence interval is fairly close to 0. And this also corresponds to our previous results here, where significance level was only p less than 0.05. So not a strong effect and not a very trustworthy result. Okay, so when you present the results of your t-test, ideally you would need to give descriptive statistics, the mean and standard deviation for each group being compared, the size of each group being compared, student t value, and Cohen's d. However, if you don't have much space in your paper, at least give Cohen's d, p level, and the size of the groups compared should be evident. And you can present your results in a neat table, for example, like this table from the APA Publication Manual 6th edition, which shows us that in one table we can summarize data from several experiments comparing two groups. And here you have sizes of the groups and the names of the groups being compared. And for each group you have mean standard deviation. And for the comparison you have T and Cohen's d estimate. And significance here is marked approximately with asterisks. This is fine as long as you have all the other information that you might need to recover this significance if you want. So these were parametric tests. Student t-test. What about its non-parametric alternatives? For independent samples, we have Mann-Whitney's test, and for dependent samples, we have Wilcoxon signed ranks test. And they both live in SPSS in Analyze Non-Parametrics menu. Basically, when you go in SPSS to analyze non-parametric tests, you have these automated newer dialogues which kind of try to pick the test for you based on what SPSS knows about your data. I don't like this approach very much because I find it too confusing. I normally personally use this legacy dialog where I can choose which test I want to run. Is it chi-square or binomial tests or Kolmogorov-Smirnov for one sample? Or different tests for two independent samples. This is where Mann-Whitney can be found. Or for two related samples. This is where Wilcoxon test can be found. And of course, if the number of samples you're comparing is more than 2, k independent or k related samples, corresponding non-parametric tests live under this dialog. I will not go into many details about these tests because basically the interpretation is quite straightforward. You look at significance level to determine whether this difference is statistically significant, and you look at your descriptive statistics to see in which group the score is higher or lower. The only tricky point concerning non-parametric statistics concerns effect size estimates. Because for Mann-Whitney and for Wilcoxon, it's not so straightforward how to calculate an effect size. You can convert the results of Mann-Whitney and Wilcoxon signed rank tests to an R effect size using this formula or using this very simple formula, because Mann-Whitney and Wilcoxon tests provide you a z-score which corresponds to your significance of the differences between two groups. And if you divide this z-score by the square root of your combined sample size, you get an approximate estimate of effect size in R units, in correlation units, which you can use to compare the results of different analyses. And you can convert this R to D or convert your Cohen's d to R, and this way you can compare the results of different tests, parametric and non-parametric ones. The only tricky point is that this is an estimate. So this effect size might be much higher than the D you would calculate by hand from mean and standard deviation. And this is okay because it is based on assumption about an ordinal scale. So the conventional D calculated based on means and standard deviations will not be quite applicable to this case. But you might find some. So if you find some strange discrepancies, this is due to this situation. And the only little warning that I need to make to those who are using R is that in R, the Mann-Whitney test is called Wilcoxon rank sum test. And Wilcoxon test, which we call Wilcoxon test, normally is called Wilcoxon signed rank test. So basically both of them are Wilcoxon, and even the function to call them is the same Wilcox test. So just be careful. It's very confusing. I don't know why they called Mann-Whitney test Wilcoxon rank sum test. So when you publish the results of these non-parametric tests, you can give for each variable a raw statistic like Mann-Whitney U or Wilcoxon W, depending on which test you're applying. a z, which corresponds to a significance. Like here, for example, z-score is 2.95. It's above the critical value of 1.96, which suggests that this is significant at p less than 0.05. And it's also above the critical value of 2.58, which means that this result is significant at p less than 0.01 level of significance. And here you see an exact significance estimate, 0.003, which suggests that it's a strongly different score in two groups. And you can use this to calculate effect size. Just divide this z by the square root of your total sample size, and you will get an R estimate. So to summarize, we have student t-tests for independent and dependent samples. We also have its robust version, which is called Welch test, which is better in most situations. But in case if your scale is ordinal, or in case if your distributions are strongly non-normal, it's best to use Mann-Whitney test or Wilcoxon test, because your statistical power to detect the effect that you're looking for will be higher. However, the disadvantage is that effect sizes that you will get will be only kind of approximate estimates, and it will be harder to compare your findings to other studies. And I hope that you'll practice using those tests in your seminars.